Welcome to the Marathon Runner. Let's just dive right into this explainer, because today we are decoding exactly what Cambridge IGCSE physics examiners are desperately looking for when they grade one of the most notoriously tricky topics on the syllabus, radiation properties. Look at the title on your screen right now. Why are we calling this the Marathon Runner? Well, because sitting at Cambridge physics exam, specifically for syllabus codes like 0625, it's absolutely not a sprint. It's a grueling, high-stakes endurance test of your cognitive energy management. It's about pacing yourself, it's about strategic planning for the long haul. And today, we are hyper-focusing on the deflection of alpha, beta, and gamma particles in electric and magnetic fields, plus the explanation of their relative ionizing effects. Now, to set the stage, I want you to picture two archetypal students sitting down to take this paper. Let's call them Alex and Sam. Now, Alex is incredibly smart. Alex knows literally every single physics fact in the textbook. But when the timer starts, Alex panics and overloads the answer page with raw data, just dumping massive paragraphs of unorganized definitions with absolutely zero analytical structure. And then on the other hand, we have Sam. Sam rushes. Sam looks at the ticking clock, completely misses the specific command word in the prompt, and writes answers that are, factually true, but totally irrelevant to what the examiner actually asked. Throughout this session, we're going to look at their flawed approaches, understand exactly why they bleed easy marks, and more importantly, show you how to transform those red pen marks into perfect green check marks. Now, what's really fascinating here is this direct insider quote from a senior examiner. They're telling us flat out that the core challenge isn't just knowing the physics. The real challenge is mastering the exact methodology that examiners are programmed to reward. Think about our two students, Alex and Sam, for a second. If a question asks them to explain the relative ionizing effects of alpha and beta particles with reference to kinetic energy and charge, Alex is going to write a 500-word novel about the historical discovery of radioactivity, the makeup of the nucleus, and some vague stuff about energy. 0 marks for the extra fluff. Sam just scribbles, alpha has more charge, so it ionizes more. Both of them just lost massive easy marks. Alex loses them for a total lack of focus, and Sam loses them for a total lack of depth. What the senior examiner is screaming at us is that the Cambridge grading scheme does not reward you just for knowing things. It rewards the highly structured, precise deployment of specific physics terminology in direct response to the command word. Literally, you could be a physics genius, but if you don't understand the rules of this specific game, you're going to fail the paper. By the end of this explainer, you're going to have the exact strategies so you never drop those easy marks again.
All right, let's move into Section 1, Core Radiation Principles. We really need to build the theoretical architecture of the syllabus in your mind before you even think about opening a past paper.
This breaks down the 3 distinct cognitive domains that examiners are targeting. This means your answers have to go way, way beyond simple memorization. You need actual application and deep analysis. So let's break this down. The first domain is knowledge and understanding. This is your baseline, right? Like, do you know that an alpha particle is a helium nucleus? Great. The second domain is application. Can you take that knowledge and actually apply it to a totally unseen scenario? And the third, the toughest one, is analysis. Can you break down a complex system, let's say a cloud chamber placed in a magnetic field, and logically deduce which track belongs to which particle just by looking at the radius of the curvature? To hit all 3 of these domains perfectly, top-tier students use a structured answering system. We call it the PEEL framework. That stands for point, evidence, explanation, link. When you use PEEL, you make your point. You back it up with evidence from the data, you offer a detailed explanation of the physics, and you link it right back to the command word. Before we continue and get into exactly how to apply this framework to cross-topic connections, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so imagine 2 answers. Answer A just lists random facts about alpha particles. But answer B makes a definitive point, uses Fleming's left-hand rule as evidence, explains the physics of the charge, and links it back. If you're structuring your thoughts like answer B, you are already miles ahead of the competition.
So the absolute crucial takeaway here is that principal examiner reports explicitly state, like they literally put it in bold, that candidates who demonstrate causal relationships and cross-topic connections get significantly higher marks than those who just recite definitions. Look at the isolated definition side. This is classic Alex. Alex writes, an alpha particle has a charge of +2 and a high mass. Kinetic energy is half mv squared. Is it true? Yes. Is it worth maximum marks? Absolutely not. Now look at the other side, cross-topic connections. This is the gold standard. This is where you connect kinetic energy and electric charge directly to relative ionizing effects. Think about it conversationally. An alpha particle has a massive +2e charge and a really large mass. Because it's so heavy, for any given amount of kinetic energy, it's traveling much, much slower than a tiny lightweight beta particle. Now follow the causal chain here. Because it's moving slower, and because it has that double positive charge, it spends more time near the atoms it passes through. It exerts a massive electrostatic force on those orbital electrons. It literally violently rips those electrons away, dumping its kinetic energy incredibly fast over a very short distance. See? That cross-topic connection completely explains why alpha is highly ionizing but has terrible penetration. It's a beautiful logical narrative. It's not just a disjointed list of textbook facts.
Moving right along to Section 2, Deflection and Ionizing Effects. This is where we build out our analytical framework and apply those cognitive domains directly to alpha, beta, and gamma radiation.
This maps out the exact comparisons you have to make. But listen to me carefully here. Examiners demand that you identify both similarities and differences, and you have to use specific comparative connectives backed up by hard evidence like kinetic energy and electric charge. Let's talk about deflection in an electric field. We know alpha particles are positive, so they deflect towards the negative plate. Beta particles are negative, so they deflect towards the positive plate. Gamma rays, they're neutral electromagnetic waves, so they just cruise straight through, totally undeflected. But if you just write that on your exam, you are leaving marks on the table. You have to use comparative connectives. You need to say something like, whereas alpha deflects towards the negative plate, beta deflects towards the positive plate and undergoes a much larger deflection due to its significantly smaller mass. Bam! That's how you get the mark. Now, think about magnetic fields in Fleming's left-hand rule. The magnetic force equals magnetic flux density times charge times velocity. The acceleration is that force divided by the mass. Because a beta particle has a mass thousands of times smaller than an alpha particle, its acceleration is insane. So its deflection curve is dramatically sharper, even though its actual charge is smaller. If our rushing student Sam was answering this, Sam will just say, they bend in opposite directions. Sam completely misses the mark for not comparing the radius of the curvature based on the mass-to-charge ratio. You have to weave these concepts together.
Okay, Section 3, the technical methodology. Now we're getting into the real mechanics of executing this procedural framework so you can translate all this theory into maximum marks. This illustrates the 5-step procedural framework you have to deploy for every single question. This is how you ensure your data interpretation hits the highest evaluative levels. Let's actually run a live hypothetical scenario through this blueprint. Step 1, deconstruct the question. Let's say the command word is compare. Boom. That instantly means we must state similarities and differences. Step 2, extract relevant data. The prompt gives us an alpha source and a beta source with the exact same initial kinetic energy. Step 3, select your framework. We're going to use our Peel framework, focusing on the causal relationship between charge, mass, speed, and ionization. Step 4, execute with clear notation. Mentally or in the margins, write out your physics equations. Kinetic energy equals half mv squared. Step 5, present with correct terminology. Watch how a messy paragraph magically transforms into a laser-focused, Peel-structured masterpiece. Point, alpha particles have a higher relative ionizing effect than beta particles. Evidence, alpha has a +2e charge and large mass, while beta has a -1e charge and negligible mass. Explanation, for the exact same kinetic energy, the more massive alpha particle travels at a lower velocity. This lower velocity, combined with a greater electric charge, means the alpha particle exerts a stronger electrostatic force over a longer interaction time with atomic electrons, causing way more frequent ionization events. Link, therefore, this rapid loss of kinetic energy explains why alpha is far more ionizing and less penetrating than beta. See that? Maximum marks secured.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, getting back into it, the absolute critical point here is that high-level data interpretation requires you to constantly extract information from complex data sources, interpret the unseen relationships, and draw strictly evidence-based conclusions. You cannot, I repeat, you cannot just rely on rote memory here. The exam board is going to throw unfamiliar data sets at you. They'll give you weird isotopes or novel experimental setups you've never seen before. It's a test to see if you can extract the variables, like reading a specific kinetic energy value off a totally new graph, and map it back to your core principles. That ability right there is the sole difference between an A-star student and a C student. You have to be relentless. Your conclusions must be anchored entirely in the evidence they provide you.
Let's move to Section 4, Top Examiner Warnings. We're going to dig into the actual principal examiner reports to see where capable, smart students are just throwing away their grades.
This is the million-dollar question examiners ask every single year when they review underperforming test papers. Why is interpreting this data so hard? I want to run a little challenge with you right now. I'm going to read a sample paragraph written by our rushing student Sam. I want you to listen really closely and try to identify exactly which sentence is losing marks and why. Ready? Here we go. The magnetic field pushes the alpha particle up and the beta particle down. Gamma goes straight. Alpha is heavy, so it doesn't bend much, but beta is light, so it bends a lot. This proves their charges. Okay, time's up. Did you catch it? What command words are completely ignored? What physics terminology is completely missing? Let's look at the examiner's feedback. The fundamental flaw is the entirely non-technical language. Pushes up and pushes down are not physics terms, guys. The examiner wants to read deflects in opposite directions governed by Fleming's left-hand rule. How about heavy and light? Nope. That should be large mass and negligible mass. What about doesn't bend much? Come on, that needs to be has a larger radius of curvature. This right here is why students find it hard. They write their answers like they're texting a friend, not like they are proving a complex scientific principle to a Cambridge examiner.
The principal examiner reports highlight these exact 3 mistakes year after year, and it proves that students aren't failing because they don't know the physics, they're failing the presentation and the context requirements. Mistake number 1, forgetting proper formats. That basically means you completely abandon the Peel framework we just talked about. Mistake number 2, forgetting to check your presentation. Now, this sounds basic, but I'm talking about sloppy handwriting. If your beta symbol looks like a capital B or your alpha symbol looks like a messy lowercase a, the examiners will not give you the benefit of the doubt. They will just mark it wrong. And mistake number 3, providing generic answers that aren't specific to the context. Listen, if the question asks about a specific isotope emitting beta particles inside a vacuum chamber, your answer better specifically reference that vacuum chamber. You can't just recite a generic textbook definition of beta decay. Every single sentence you write has to be a deliberate dodge of these 3 traps.
Which brings us to Section 5, the method marks strategy. This is it. This is your ultimate exam safety net. Because look, even with the best frameworks, you are human. You're running a marathon. You're going to get tired.
This illustrates the deconstruct, solve, and evaluate protocol. It absolutely forces you to show your analytical framework to the examiner at every single step. Think about our 3 rules that guarantee top marks. Rule 1, command word decoding. You let the specific word dictate your entire structure. Rule 2, Peel framework application. Rule 3, the time management matrix. You need to be allocating exactly 1 minute per mark available. By explicitly identifying the given information at the top of your workspace, breaking your math down into highly logical, numbered steps, and then actually stepping back to check if your final answer is physically reasonable, you are building a fortress around your grade. Seriously, if you do a calculation and find out your alpha particle is supposedly traveling faster than the speed of light, step 3 is what forces you to stop, check for reasonableness, and catch your own math error before the examiner does. And this is the crucial point, an explicit warning straight from the people grading your paper. Showing you're working is not optional. It is absolutely mandatory. Method marks are your safety net for when a calculation inevitably goes wrong. Let's say you have a 5-mark calculation question about the kinetic energy of a deflected beta particle. The final correct number at the bottom of the page, that's usually only worth 1 single mark. The other 4 marks are given to you just for showing the correct equations, substituting the right numbers, and demonstrating a logical mathematical progression. If you just aggressively punch numbers into your calculator and write down the wrong final answer, you get a 0 out of 5. But if you take 30 seconds to write out the formula, show the substituted values, and then make a dumb calculator typo, you still get 4 out of 5 marks. That is the method mark strategy in action, and it is quite literally the most important exam habit you can ever build. So, as we wrap up this explainer, I want you to ask yourself, are you going to utilize the method mark strategy and this procedural framework to secure maximum points on your next physics paper? You are no longer Alex, just indiscriminately dumping irrelevant facts on the page. And you are certainly no longer Sam, rushing and totally missing the point of the command words. You are a marathon runner now. You know how to pace yourself, you know how to apply the framework, and you are not going to leave a single easy mark behind. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep studying smart, and we'll see you next time.